In this video, we are going to be working two problems with projectiles. The first problem is going to be a problem that combines one-dimensional and two-dimensional kinematics. And then the second problem is just going to be a straight two-dimensional kinematics projectile problem. This first problem is actually a little bit more complicated, so make sure you're thinking very deeply as we go through this. In our first problem, a firework is launching into the air using a rocket that's accelerating it in a straight line for the first 15 meters of its flight at 75 degrees above the horizontal. Now, there's two parts to what I just said that are important. It's moving in a straight line at a constant acceleration for the first 15 meters of its flight because it has a rocket that's burning, and the rocket is going to be the thing that is providing most of the reason for this thing to move. And the rocket's going to just push it in a straight line. It's apparently being launched at an angle 75 degrees above the horizontal. But just because it's being launched at an angle doesn't mean it's not being launched in a straight line. This is still one-dimensional straight line motion. It just has a two-dimensional flavor to it because it's at 75 degrees above the horizontal. We're going to have to deal with that when it comes. But the key is that the kinematics here, the actual kinematics here, is one-dimensional kinematics. Straight line, one-dimensional acceleration for the first 15 meters of flight. And this is a rocket. And what should you expect from a rocket? Large explosive accelerations. So we're going to have a very large acceleration to begin. Our rocket is going to attain a very high speed in a short period of time with a large acceleration. That's what fireworks do. Once the rocket burns out, then this firework is going to move like a projectile. It's going to have been launched into the air at a high rate of speed with a certain trajectory, still 75 degrees above the horizontal. But now the rocket's no longer propelling it upward, and gravity is going to act to pull the firework downward like a projectile. The fuse is still burning, and that fuse is going to run out at the maximum height of the firework, and it's going to explode in the air. The things we're going to be asked to find are three different things. First of all, the height at which the firework explodes. Thankfully, that's its maximum height, so that's probably going to be pretty easy to calculate with, because I know that the velocity in the y dimension at the maximum height is going to be 0. And that gives me some extra equations that I can use that might make this easy to solve. The time from launch to the explosion, well, that's interesting because that's the total time, including the time when it was moving in one dimension at 75 degrees above the horizontal, and the time it was moving like a projectile. And then the x displacement from launch. So again, the entire x displacement, including when it was moving at 75 degrees but in a straight line, and when it was moving like a projectile. Okay, so what does this look like? Maybe if we draw this out, it'll make a little more sense, and I'll be able to see the two parts to this problem as well as the two dimensions. First of all, here's my rocket, and my rocket's going to travel up into the air a pretty large distance and explode. First of all, we have the burn distance of the rocket, where it's actually going to be accelerating in that straight line. Now keep in mind, when I say it's accelerating in a straight line, we're going to be dealing with one-dimensional kinematics along that flight path. But we are not actually moving straight up into the air like we do in a lot of one-dimensional kinematics problems. This rocket is going to be covering some horizontal distance and mostly vertical distance as it moves at an angle of 75 degrees above the horizontal. So we are going to have to keep in mind that this rocket, even though it's moving in a straight line, because it's at an angle, it's covering some horizontal distance. We're going to need to figure out how much of that distance covered is horizontal and how much is vertical. And we're going to do that relatively early in the problem. Then after 15 meters, the rocket stops burning, and it's just going to be continuing to move upward, but at a decelerating rate because of gravity. That's going to look like this. It's going to move in a parabolic way as it continues to move at the same speed in the x dimension, but is slowing down in the y dimension. And when it slows down to rest in the y dimension is when the fuse is going to ignite the firework and it's going to blow up. And we're trying to figure out how long that takes, what that height actually is, and also the x displacement of it from where it was originally launched. Okay, this is showing that even though my 15 meters covered at the beginning is in a straight line, there's still going to be some x distance and some y distance covered by this. And we're going to just go ahead and calculate those right now because it's a fairly straightforward calculation. So these are displacement vectors. Notice that I'm using x, y, and then the resultant r. I'm not using velocity vectors. I'm using displacement vectors. So I'm going to calculate something that's a distance when I use these vectors together. And as I look at these three vectors, is there any of these values that I know? Well, I know that the r value is 15 meters. And if I multiply that r value, 15 meters, times the cosine of 75 degrees, that will return the length of the adjacent side, or that x value. And if I get the value of my x vector calculated, I find that it's 3.9 meters. And just, this is for later. This isn't important for the kinematics of the rocket, but it is important for its geometry. I find that during the burn, during that 15 meters it was moving at 75 degrees above the horizontal, it covered 3.9 meters horizontally. And I'm just going to tuck that information away for right now in my diagram so I have it later. I'm going to do the same calculation in the y dimension, except in the y dimension, because I have the opposite angle from that y leg of the triangle, I'm going to use the sine of theta. Sine of theta is the ratio of the opposite side to the hypotenuse, or using the values that I have in my diagram, the resultant magnitude times the sine of theta is going to give me the y value. And if I plug those values in, 15 times the sine of 75 degrees is 14.5 meters. And I'm just going to pause a moment to make sure this makes sense as I put it in my diagram. Does it make sense that most of the distance covered is y distance and a relatively smaller x distance is being covered? 75 degrees is a very steep angle. It's not that far off of 90 degrees. So I would expect that the y value is going to be greater than the x value. Yes, that makes sense. Okay, so let's start to keep track of my one-dimensional kinematics part of the problem. What are the things that I know in this one dimension? Now that I've got those two component vectors for the displacement of 15 meters made, I'm going to switch my mind back to one-dimensional kinematics mode, because we're just looking at the path of the rocket as it's traveling along that actual 15 meters. The only reason I needed those components is for later when I need to figure out the total x distance covered and the total y distance. But that was just a little extra step that I had to do. Now we're going back to one-dimensional kinematics. Notice I don't have a separate column for x and y in my table. All I care about is the values along the path that the rocket is actually moving. So my original y value, and I'm calling it y because at 75 degrees this is mostly vertical. So I'm just going to refer to these as y values. My initial y is 0 meters. My final y is 15 meters. Notice that I'm going along the actual path that the rocket is moving in order to calculate the amount of time it's going to take to cover this 15 meters. All right, the next thing I'm going to do is note my initial velocity. When the rocket starts burning, the moment after it starts burning, its initial velocity is 0, but it very, very quickly attains a velocity of 70 meters per second. It's not going to take a long time. It did it within 15 meters of distance. Now, I need the acceleration and the time, but those are two values that I don't know. So I'm going to have to calculate both of those values using one-dimensional kinematics equations. So if I know that I went from 0 meters to 15 meters, and in that distance, my rocket accelerated at a constant acceleration from 0 meters per second to 70 meters per second, what is my acceleration? Is there an equation that I have that will calculate that for me? Well, I could use the Vy squared equals 2a change in position equation. And what do I know in this equation? Well, first of all, is there anything that goes to 0? My YO is 0, and my original Y velocity is 0. So I'm just going to go ahead and cross those two values off. I know they're going to be 0. Plug in the values that I know. My y velocity at the end of this acceleration is 70 meters per second. I need to square that value, and that's going to equal 2 times the acceleration times the distance covered of 15 meters. Rearranging to solve for the acceleration, it's 70 squared divided by 2 times 15, and I see that this is going to be a large number with 70 squared in the numerator, and it certainly is a large acceleration, 163 meters per second squared. We don't oftentimes see accelerations that large, so does that large value make sense in context here? Well, it does, because this is a rocket, and rockets accelerate very, very quickly. Not only that, it's a rocket with a very small mass, a firework, so it's capable of accelerating that fast. I'm going to plug that value into my table, and now we can use that value to find the time. How am I going to do that? Well, the simplest equation is this one, velocity, acceleration, time. This is my definition of acceleration equation. Is anything going to go to 0 here? Well, I noticed that my original y velocity is still 0. So this is going to be a very simple equation to solve. Plug in what I know. 70 equals 163 times time, or time is 70 divided by 163, 0.43 seconds. So in the one-dimensional section of this problem, the time it takes for the rocket to move that first 15 meters is 0.43 seconds. Everything I've done so far is just the one-dimensional kinematics for the first part of this problem, so I can get a tally of the amount of time it takes for the rocket to get through that first 15 meters, and also the x and the y distance. And now that I have those initial values, I'm going to now analyze the rocket once it becomes a projectile, and then later I can come back and add in these initial values. These are two completely separate parts of the problem, though, and I'm going to treat them completely separately in my strategy for solving. So now, let's consider the projectile part of the problem when the rocket's motor is burned out and it's going to start falling back down toward the Earth. To do that, because it's a projectile, now I have to consider both x and y dimensions. It's no longer just moving in one dimension. I'm going to have constant x speed with constant y acceleration, like all projectiles. So I need to account for both columns here. And what do I know? Well, first of all, I'm just going to reset my original position in the x and y dimensions to 0 for this part of the problem. You may be asking yourself, well, couldn't you have plugged in the 3.9 and the 14.5? Yes, that certainly would work to plug in those values as my initial values here and then solve the rest of the problem. It's just the equations are a lot more streamlined when you start at 0, 0. So I'm going to reset my reference point. I'm going to work this like it's an entirely separate problem. And then at the end, I'm just going to go back in and add those initial distances and the initial time instead of accounting for them here. All right, what about my final x and my final y position? Those are both unknowns in this problem, and both unknowns that I'm going to need to find, because I'm asked what the x displacement is and what the height at which the firework explodes is. All right, what about the initial velocities? This is another case where I'm going to use vectors to solve for these unknown values. I have a velocity at an angle of 75 degrees. I can find the x and the y components of that velocity. Notice that now I'm working with velocity vectors, not displacement vectors. So what I'm doing now is fundamentally different from what I was doing before. If I'm working with a velocity at an angle, the component vectors are also going to be velocity vectors. When I add vectors together, I can only add them together if they have the same units. So these all have to be velocity vectors. And am I able to use trig to figure out what the initial x and the initial y velocities are? Well, I sure am. In the x dimension, again, I'm going to use the cosine because once again, I have that bottom angle and the x dimension side is adjacent to that bottom angle. So I'm going to plug in the values from my triangle, and I'm going to actually solve by multiplying 70, which is my initial velocity at an angle, times the cosine of 75 degrees, That gives me 18.1 meters per second. I'm going to go ahead and log that in my table as my initial x velocity. Because I know I'm dealing with a projectile, I know that my final x velocity is going to be the same as the initial because there's no acceleration in the x dimension. So it's a constant velocity problem in the x dimension. In the y dimension, I'm going to use the same technique to solve trigonometry, except now I'm going to use sine instead of cosine because I'm looking for the opposite side. So I'm going to rearrange the equation again to solve for that opposite side. V times the sine of theta instead of cosine theta. And when I plug in my values to solve that, I find that the opposite side is 67.6 meters per second. Does it make sense, again, that my vertical speed component is going to be much greater than my horizontal speed component? We're looking at 67.6 in the vertical and just 18.1 in the horizontal. Yes, it makes sense, again, because 75 is a very steep angle, so I would expect the opposite side to be longer than the adjacent side. Also, what's happening? Do I have the same velocity the entire time throughout this problem in my y dimension, the same as my x dimension? Well, no, because there's acceleration due to gravity in the y dimension. So I'm going to fill in 67.6 into my table as my original y velocity. My final y velocity is also known because I'm looking for the maximum height when the firework explodes. And at that maximum height, the velocity is going to be 0. The acceleration is negative 9.80 meters per second squared. And unlike in previous problems where we worked a time in one part and then plugged that time into the next part of the problem, I am not, in this problem, I am not plugging in that 0.43 seconds from the first part in for my time here. The time for the projectile part of this problem is one of my unknowns. I don't know how long it's going to take to get to that maximum height from what's given in the problem. Remember that 0.43 seconds is just the time it took for the rocket to burn out so that it's launching like a projectile. That's a completely separate time frame than the time frame when it's moving like a projectile. So once that 0.43 seconds ends, a new time frame begins, and I can't carry it over to the next part of the problem. All right, now looking at this, I know equally the same number of variables in the x dimension as the y dimension. And that tells me that I can probably start solving in either dimension, whichever one I choose. I'm going to start in the y dimension. And in the y dimension, I need to find my time and the final height. Let's start with time. So I can use this simple definition of acceleration equation to solve for time by plugging in everything I know. Is anything going to go to 0? Well, in this case, my final velocity is 0. So I'm going to have the expression 0 equals 6.67 meters per second minus 9.8 meters per second squared times time. Keep in mind, it's only minus because 9.80 meters per second was negative. So I could have written plus negative 9.8 meters per second squared. I just chose to use the minus sign out front instead as my operation. I'm going to get t on a side by itself by subtracting 67.6 from both sides and dividing by negative 9.8. And I find that there is a time of 6.90 seconds. Now, that seems like a long amount of time for the y dimension. Usually y dimension things happen pretty quickly because gravity accelerates things so quickly. But keep in mind, this is a firework, and there is quite a bit of time between when you launch a firework. You can hear the boom of the fireworks rocket motor being lit, and then it takes several seconds before you see the firework actually explode in the sky. So it can be a length that's this long. This does make sense. I'm going to plug that in for my projectile motion data. Now, what about x and y? Well, we're working in the y dimension, so let's find what y, the actual y position is at the maximum of my parabola. I'm going to go ahead and use the position time equation with acceleration, and I'm just going to plug in everything I know except for y0, which is 0. That makes this a little bit easier to solve, but there's still quite a few variables to keep track of. I'm going to multiply this out, being very careful to remember to square my second time, 1/2 at squared. And then when I calculate with these values, I find that my firework reaches a height in this part of the problem of 233 meters above where the rocket burned out. So it's just the projectile is going to continue moving upward in the air for 233 additional meters. I'm going to plug that into my table. And now let's finish up by solving in the x dimension. In the x dimension, the equation is always simple because I think about what in this equation goes to 0. There's no acceleration. And in my x dimension, the way I have this set up, there's no original position. So my x is simply going to be velocity times time. 18.1 meters per second, my horizontal velocity, times that 6.90 seconds until it reaches its maximum height. But in the x dimension, it's just going to be traveling along at a constant rate horizontally. So it's going to move 125 meters in the x dimension. I'm going to plug that into my table to keep track of it. Now, I'm not done with the problem yet because I need to calculate the total height when the firework explodes, the total time from launch to explosion, and the x displacement, total x displacement. So I've got information in two different tables, and now I need to put it all together. So to calculate my total height, I need to add together the height during launch, 14.5 meters in the y dimension, plus the height when it was a projectile, that's where it gained most of its height, 233 meters. When I add those values together, I get a final height of 248 meters, and that's what I would report for A. What about the time? Well, to get the total time, I need to add together the launch time when the rocket was burning and the projectile time after the rocket stopped burning while it was only being affected by gravity. 0.43 seconds plus 6.9 seconds, a total time from launch to explosion of 7.33 seconds. And then finally, what about my total x displacement from where it was launched to the x position underneath where the rocket exploded in the air? Well, that's the same sort of calculation, 15 meters plus 67.6 meters for a total of 83 meters. And I've completely solved this problem for all of the relevant values. The tricky thing about this problem is it was a two-part problem and a two-dimensional problem. And it's difficult to determine that it's a two-part problem starting with one-dimensional kinematics, but as you get good at working with physics, you should be able to determine that there are two different kinds of motion happening here, and you need to solve for each one individually. All right, let's take a look at another problem. This is a much more straightforward problem, only one part. College physics student forgets her keys in her third-floor dorm room and texts her roommate asking her to throw the keys down from the window 14 meters above the ground. The roommate tosses the keys with an initial velocity of 1.44 meters per second, a very slow initial velocity, but it's not like the roommate is trying to really pelt her other roommate with these keys. So you would expect it to be a nice gentle throw at an angle 15 degrees below the horizontal. So she's throwing them downward toward the physics student. What are we trying to find here? Assuming the window is flush with the building, so the window is at the same distance from our physics student as the building is, how far away from the building should the student stand to catch the keys? This is an x displacement question. How far away from the building is she going to stand? Now, this seems like a horizontally launched problem, except it's not horizontal. The roommate is throwing them downward at an angle. And even if something is thrown downward, it has initial x and y components that we're going to have to deal with. So let's take a look at what the setup for this is. Here's the dorm. Here's our student. And here's the path that the keys are going to follow toward the ground. Notice that the keys actually start not at the maximum of a parabola, but beyond the maximum of a parabola. The parabola is already decreasing because the keys are thrown downward. How are we going to account for the keys being thrown downward? Well, it's the same as the way that we account for things being launched upward at an angle too. We're going to set up a vector diagram and look at the component vectors. So these keys are being thrown downward at an angle 15 degrees below the horizontal with an initial speed 1.44 meters per second. I can find the x and the y components of this vector, knowing that it's 15 degrees, and then I will know with what x velocity these keys were thrown and the initial y velocity, which will help me to solve the problem. The next step is the important one for any type of problem like this. I need to account for everything that I know. So let's see what I know in this problem. Do I know the original x position? Yes, we're going to say that the building is our 0 meter mark. Okay, that's our reference position in the x dimension. In the y dimension, we're starting 14 meters above the ground. So let's make the ground our 0 position, and our window is going to be 14 meters above that. That's my original y. My final x is unknown. That's what I'm looking for. How far away from the building do I need to stand to catch these keys? My final y is known because it's at the ground. Okay, so we're going to assume that the keys go all the way down to the ground just to simplify. It doesn't tell me what the height of the physics student is. If I knew the height of the physics student, I could set that height to 0. But not knowing the height of the physics student, I'm just going to assume that I'm going to stand on that point on the ground to catch the keys. The original x and y velocities are going to come from the vector diagram, just like they always do. So let's go ahead and solve for those initial x and y velocities. We'll start with x. In the x dimension, just like before, I'm given the same basic angle. It's that bottom angle, the angle attached to the x-axis. And I'm looking for, in the x dimension, the side adjacent to that angle in that right triangle. So I'm just going to plug in the values from the diagram. Again, I'm working with velocity values here. Plug in what I actually know, and then when I punch it into a calculator to solve it, I find that my initial x velocity is 1.39 meters per second. I'll put that value in my diagram, and I'll also record it in my table. Now keep in mind that 1.39 in the x dimension is the initial velocity and the final velocity in the x dimension, because in the x dimension the acceleration is 0. So I'm just going to record all of that in my table right now. What about my y dimension original velocity? Well, I'm going to use the same technique, but again, I'm going to use sinus and a cosine, and this one's going to be just a little bit different if you choose for it to be. So my equation looks like this, and what am I going to plug in for theta? Well, my angle is 15 degrees, so I could just go ahead and plug in that 15 degrees, and then my sine function, sine of 15 times 1.44 is going to return 0.37 meters per second. I can go ahead and put that in my diagram, but let's think about what that is. That's a downward vector, and downward vectors should be negative. Is there a way for me to get this to return a negative? Well, if you punch in your calculator, instead of the sine of 15 degrees, you punch in the sine of 345 degrees, because remember, that's measuring that vector from the positive x-axis instead of just below the x-axis. You're supposed to go counterclockwise all the way around. That will correctly give you the negative 0.37 meters per second value. Now, do you need to have that negative returned by your sine function equation? No. You can just remember that it's negative, but you have to remember if it's a downward facing vector or a vector to the left, you have to record that it's negative in your data table. It's going to be important for me to keep track of that as a negative velocity. And the reason for that, this roommate is throwing the keys downward a bit. So they're starting off with a bit of downward y velocity to begin with. They have a velocity in the x dimension and a little bit of downward velocity in the y dimension. And then we're just going to finish this up. Do I know the final x velocity? No, and I don't believe I'm going to solve it in this problem, although it might be nice for the roommate to know what her keys, the speed that the keys are going to hit her hand at, to make a decision whether or not she actually wants to catch them. And the acceleration is going to be acceleration due to gravity, negative 9.80 meters per second squared. I do not know the time, but that's something that I can find in the course of solving this problem if I choose. Now, looking at this table of knowns and unknowns, I realize that I have the same number of unknowns in both columns. But y has more functional knowns than x does. Remember that one thing I don't know in the y dimension is something I'm probably not going to be looking for anyway. Anytime we solve in the y dimension, we typically will exclude one value we're not interested in. But in the x dimension, if I'm trying to use my definition of velocity equation, or constant velocity, I'm not going to be able to solve that with the two unknowns that I have. If I don't know my final distance or time, that equation is still going to have two unknowns in it. So the y dimension is the logical place to start here. And honestly, I could do this by trial and error too. I might have written out x dimension and then written my equation and tried to solve it and found out that I couldn't. So then I move over to the y dimension to see if I can solve in the y dimension. And the equation I'm going to choose is my distance time with acceleration equation. There is no term in this equation that's a zero, so I'm going to have to plug in values for everything that I know, and time is going to be my unknown. I'm going to set y equal to 0 so that I can solve this using the quadratic equation, and then I'm just going to apply the quadratic equation to this to solve. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Very important for me to keep track of that negative sign in b. Notice it's negative 0.37 meters per second. Remember that negative 0.37 came from our observation that the keys were being thrown downward. Honestly, if you were to work this problem out on your own, it's pretty easy to miss that, because it's not like there's this big revelation that that number should be negative. It just gets plugged into the quadratic formula, which is something you use to just plug and chug through the values anyway. So it's very, very important for you to proactively think as you're working the problem that anything that points downward or to the left is negative, and then keep those values consistently negative where they belong throughout the problem. All right, and now that I have everything in the right place, when I solve this, I find that the time is either negative 1.78 seconds or 1.71 seconds. I'm going to choose the positive value because that's the one that makes sense. I'm going to go ahead and plug that in for t in my table. And now I have everything that I need to solve in the x dimension. That 1.71 seconds is the time it takes for the keys to fall to the ground from the original 14 meters. And now I can go ahead and solve for how far it moves in the x dimension during that time. The equation I'll use is this simple one where I get to cross off acceleration because it's 0. I also get to cross off the original x position. I simply multiply 1.39 meters per second times 1.71 seconds. That gives me a result in meters of 2.37 meters from the building. And that's where I should probably stand and wait if I want to catch my keys. So now we've worked two different types of projectile motion practice problems. One of them where the projectile was launched with an initial upward velocity, that was a firework problem, and another where a projectile was launched with an initial downward facing velocity, that was this problem with the keys. You'll run into both kinds of problems, and a third type of problem where a projectile is launched horizontally. And then one more consideration. All of these problems that we've been working so far, the object has landed at a different height from where it started. In another type of projectile motion problem, an object is launched from the same height that it lands. But that is an investigation for another video.